Synthesis is one of the more satisfying and creative parts of organic chemistry. Um, and there's really two things that you want to become familiar with doing. One is to know your reactions and know what's possible for each functional group. Like, can you possibly substitute it with something or eliminate it to make an alkene or add something to it? You want to know what reagents are needed to do those transformations. And then oftentimes when we do synthesis, we kind of try something and it doesn't work, and then we have to try something else and do that until we find something that works. And so make sure to recognize that that process is just part of the synthesis process, and that's, it's kind of trial and error. So be patient with that. So in order to learn your reactions, index cards are helpful, and I've sent this around in the email, and it's in your modules, and here it is again. But do as we go, make sure to make index cards and keep memorizing your reactions and also their mechanisms. And so if you do that as we go, instead of waiting and kind of trying to cram it in, you'll be able to build your knowledge a little bit better. So when we start thinking about different pathways, one of the things to recognize is that there's actually a lot of different reactions that you already know. These are just the addition ones that are here, but think substitutions and eliminations and other reactions as well. So you really already have a large library of reactions, and trying to think about sort of what possible processes are to get from a starting material to a target molecule, which is what you do in synthesis. We want to recognize that there's a few standard ways to put these reactions together in ways that actually are interesting and do syntheses. And so all of this is from chapter 12, and we'll get here early next semester. But there's actually, you will be able to do all of these by the end of the semester. And now you can do the ones in the box or the ones in the boxes. And so let's just go through a couple of these and talk about how we can kind of do that trial and error methodology to figure out what a reasonable synthetic path might be. So the first one is this sort of very standard moving of a substituent like a bromine. And so you might want to ask yourself questions like, well, what's changing? And what could I do with this molecule? I mean, what does something with a bromine do? You could substitute it, right? You could eliminate it. I think that's about it. And then how do you make a highly substituted bromine? What have we seen that allows you to do that? So those are just some questions to kind of ask yourself as you think about how to go from the starting material to the target molecule. And there's not a single reaction that will do this, so you'll have to string some reactions together. And that's what the synthesis is. So, like I mentioned, I think two things that you probably think of that you can do when you see an alkyl halide like this is you could do elimination to make a double bond, or substitution to substitute the bromine with a nucleophile, maybe an OH or something like that. So those are both two possibilities, but I think only one of them, the one on top, is actually going to get you to this final product, right? Because now we can add something to this in order to give you your tertiary bromine. And so just hydrohalogenation will do that to give you your product. So now we want to go back and make sure that we put in all the reagents. And so thinking about what elimination reagent we want to use, we see that this is, it's a primary bromine. And so, we need something that's not going to do an SN2 reaction. And so if we used hydroxide, that would probably do SN2 because it's nice and small. It's a good nucleophile. So a terbutoxide, which is not a very good nucleophile, would probably be a better base to use in this case. And then that will give you that double bond. And then hydrohalogenation, remember that its regiochemistry is Markovnikov, and so it's going to give you that more substituted product, as you see over here. All right, so that's an example of a synthesis and how you might approach it. So let's just quickly look at two other examples. So here we have, in a way, there's some similarities, right? We have an alkyl halide that we're starting with, and we want to wind up with a more substituted alcohol in the end. So we're going to go through that process kind of like we went through before, right? Where we're going to eliminate and then add. And so here's an elimination, and then we want to do our addition. And since it's a Markovnikov product, we can just use the sulfuric acid catalyst with some water to give us the more substituted product. Now in this case, I did use the hydroxide. This is a secondary alkyl halide, so it's not going to be as likely to react with a nucleophile. The base will probably act like a base. And I used a small base so that it would make the more substituted product, as you can see here. All right, so that's the second one. So now let's go ahead and do one that's a few more steps. And so here we have an alcohol, which is our starting material. And again, we need to get rid of it and then add something to it. So, I mean, the idea here is still the same, that we need to do an elimination reaction, and then we want to add, get a bromine on there, but we want the bromine at the less substituted position. So there's some kind of funky things going on here. And one of them is what would happen if we just did an elimination with sulfuric acid and water. And if we did that, we'd actually get a carbocation intermediate. It's an E1 reaction. And so we would expect to get a rearrangement. So I don't think that we would actually get this product. I think we would get a rearranged alkene. So that's not really going to help us. So the question then becomes, well, how can I do this reaction? How can I do an elimination without a rearrangement? And what I would want to do is an E2 reaction. I can't do an E2 reaction in the acidic conditions that are required to get rid of an OH. So I need to make this into a better leaving group where I can use a strong base and make this a one-step reaction, like to just use a really impatient base. And so I need to make this into a better leaving group. I could make this an OTOS, a tosylate if I wanted to. I could make it a bromine. Either of those will work. Chlorine, something like that. And now I can use that hydroxide and do, well, yeah, I don't know. Actually, I'm not sure that the hydroxide would be the best choice here. I think we would use T-butoxide. And, well, actually, it wouldn't really matter because we have, we can't form a double bond right here in the middle. Because we don't have a beta hydrogen over here. So the hydroxide would have to take it from the end too. But if we wanted to avoid that an SN2 type reaction, then we would need to use like a butoxide there instead of the OH. But in any case, we can do an E2 reaction and get a non-rearranged product, which is shown there. So then we will have this weird thing where the bromine is on the terminal less substituted carbon, and that's weird because Markovnikov chemistry is the norm, and so that would put the substituent on the more substituted position. But we can get it on the less substituted by just doing hydration with that hydroboration oxidation reaction. And so if we do that, we get an OH on the end. And now we can just do a substitution reaction, an SN2, to give us our product.